So our first talk of this session will be presented by Jonathan Balkind, who is an assistant professor in computer science at UCSB. And Jonathan will present his work about prediction system service. And so if you're ready, Jonathan, please take it away.
Thanks very much. So I'm here today to talk about our prediction system service. I'm presenting from Art Club UC Santa Barbara on behalf of two of our student authors who unfortunately weren't able to make it and return to the US. So our motivation in this setting is that we're trying to tackle runtime optimization problems, specifically heuristic problems. So I don't know why it's flashing, I'll just keep going. We have a setting where we're trying to make runtime choices. Things like I have multiple paths which are functionally equivalent but performance different. And in these kinds of settings, developers are routinely developing heuristics. Unfortunately, these heuristics are becoming more complex, the settings are becoming more complex, and so it's not clear that heuristics are always the best solution. On top of that, developing heuristics themselves require domain-specific knowledge, and they don't always have the best results. So we want something where we can figure out a solution that's better than making these heuristic decisions. Now, using machine learning for system optimization is not new. There's been a lot of work in this space on things like recommendation systems, databases, and compilers. A lot of these solutions are not generally broadly applicable. We want something that's reusable, and we don't want to have to bring a new machine learning stack every time we have a new solution. On top of this, a lot of these techniques are very high cost in terms of collecting training data. If you're trying to build a heuristic in some setting, you don't necessarily have the time to gather huge amounts of training data to train a solution in advance, and we prefer to do something live. On top of this, they're often fairly long latency. You're using large models, and so oftentimes your heuristic would be very small. You would make a small computation, maybe perform some kind of comparison, and so you want something that's similarly low latency. So we want to have something that's common. We can use it across applications. We want it to be reusable for a single application, so we can, for example, learn information over time as we rerun our application, or it runs for a longer time. We want to train on the fly rather than ahead of time, and we want it to be low latency. We also want good enough accuracy that we can actually make good progress on system optimization problems. So our proposition is PSS. It's a common, simple, and shared mechanism for prediction, which can be reused across a variety of runtime tasks. And we argue that the right location for this is as a system service so that it can be used in the kernel, and so it can be used in user space and used across a variety of applications. And for us, it's important for it to be cheap and kind of good enough that it's comparable to or better than heuristics. And we were joking about calling this IKEA for a while. We also need to have a simple API, and we tried to settle on the simplest API that we could use. So here we have basically 3 functions, and 2 of them are the important ones: predict and update. We provide a set of features, and we can penalize or reward the predictor. As a proof of concept, to get started and get some results, we target binary classification. We realize this isn't applicable for all settings, and we are focusing on numeric values. As a result, we chose a really, really simple predictor. We choose a hash-based single-layer perceptron. This is widely used in hardware, and so you could imagine that you could port this into hardware instead of using it in software. And so it's very efficient in terms of the overhead in software, and it's capable of making accurate predictions in a variety of settings, including some prior work in hardware lock collision, where we also tried to tackle some solution. Now, the challenge of building a system service is that syscalls come into play, and these significantly increase the latency of the operations that we're trying to perform. And so instead of this, we try to take advantage of a mechanism called a VDSO, which allows access to a page of kernel data, but you can only access it for reading, not for writing. And so we're able to perform our predictions using the weights that are stored in the kernel, and then we can use a syscall anytime we need to update, and we can batch those updates to reduce the overhead. We show PSS operating in multiple different settings, including hardware lock collision, parameter tuning for the PyPyJIT, and page reclamation inside the Linux kernel. The former 2 of these are user applications, and the latter one is a kernel-level task. So we can actually apply this technique in a number of different settings. We can also use it in both C and Python, and really anything where you can load the VDSO against your, link it against your application. Our first use case is deciding between locks and transactional memory at runtime via prediction. So we know that in some settings we'll get really high contention if we want to use transactions, and so it's better to fall back to locks. You can see in gray here on the right-hand side the code that we add into the application to enable PSS. And whenever we see a significant overhead due to failing to complete transactions, we can penalize the model and encourage the use of locks instead. We also look at tuning of the JIT in PyPy. So this is one of the fastest Python implementations. And as a result, the JIT also has a very large number of potential parameters that we might want to use. And changing these parameters can have a significant effect on program performance. And so the developers have spent a lot of time trying to tune the parameters to be good general parameters. There's been prior work which has even adopted genetic algorithms to try and choose JIT knobs in PyPy, but these have a very high overhead. It's very expensive. With PSS, we decide to group together the parameters, and so we have 6 parameters, and we'll either be more conservative or be more aggressive. So we can kind of turn up or turn down the level of JITting that we're doing. And so it doesn't really matter what the parameter values are here, but we can choose between multiple settings. The third use case we have is a page reclaim task inside the kernel. So in the kernel, if we start to have high memory pressure in the system, the kernel will try to reclaim pages. And any pages which have modified content will need to be written out to disk first. And so anytime the disk is busy, you don't want to perform these write-backs. And so the disk has to kind of have a way to say, hey, I'm congested right now, stop sending me requests. And this was called congestion wait in Linux kernel through about 5.15. Unfortunately, this is actually a really racy thing to do. And as we've started to get really deep NVMe command queues, it was a completely useless solution. So Mel Gorman proposed a new one, which was merged into the kernel about 5.15 or 16. And I won't go into the details here, but basically what you're trying to do is identify situations where you're not making reclaim progress and turn down the amount of reclaim that you try to do and allow the system to continue otherwise. And in cases where you are being successful in getting your pages back to disk, then you can turn up the number of threads and be more aggressive. Now in Gorman's solution, which is merged into the kernel, they just choose a single threshold. 12.5% success will turn on more threads. We want to set kind of more of a variable threshold. And so you can see here through these 3 settings that you could take different approaches to applying PSS based on the heuristic situation that you have. The first results I'll talk about are from the hardware transactional lock collision experiments. And what we're showing here is the improvements in performance versus the baseline. And then we have the blue bars on the left, which are for the state-of-the-art solution in HTMBench, and then the orange bars, which are PSS. And we want to have bigger numbers here. And so what you can see is versus this state-of-the-art solution, we tend to be very comparable despite having a very simple solution based on a singular perceptron. And in some cases, we can outperform. There's a variety of spots there where we get a few % extra performance. And in the worst cases, we're not tending to get more than, say, a fraction of a % downside in terms of loss versus the baseline. We also look at our JIT tuning through some micro benchmarks first. And you can see here that almost entirely across the board, we see improvements in performance over the PyPy JIT in tuning the parameters. We have a couple of cases. Our maximum slowdown is about 6%, but our maximum speed up is over 120%. We get, on average, about 15% improvement and a geo mean slightly below that. But what about real applications? So we have some macro benchmarks as well. So AIO HTTP is our first example. And here we can compare and understand what the cost of having expensive prediction is. So our syscall here in yellow is showing the cost it would be if you use syscalls for all your predictions, which might be comparable to using a heavier weight prediction mechanism. You can see in blue the baseline from PyPy, and then in red is our VDSO-based solution. And this has a significant improvement in latency, and it does improve over PyPy, whereas the syscall-based mechanism does not, which suggests that latency is important. We get about a 22% improvement here in performance. And our second benchmark here, G-Unicorn, you can see that both PSS with and without the syscall improve over the baseline, and we get about an 18.66% improvement. We also have 2 other macro benchmarks where we have lower improvements, around about 2.5% for Django CMS, and about 6% for Flask blogging. So this seems to work fairly well for PyPy JIT tuning. Lastly, for page reclaim, and this one again is inside the Linux kernel. We're moving left to right, we're increasing the number of threads, causing memory contention. So we see more congestion toward the right. And in blue, we have Gorman's solution. In the other colors, we have PSS, compared to what used to be in the Linux kernel. And Gorman's solution is what's there now. And you can see that we do about as well, or in several cases better than Gorman's solution, which is already merged into the Linux kernel. And as we go from left to right through the PSS solutions, we also show running multiple iterations and keeping the weights that we learn across those iterations. So over time, we're gaining better predictive knowledge. And we can see for cases like mmap 21, 30, and 48, that we actually gain some knowledge over time and improve the quality of the predictions by rerunning the application. So in conclusion here, we've built a high level of abstraction to enable the programmer to tackle a variety of different runtime optimization problems. We use a VDSL-based approach, which can be low latency, and it gives us better overhead than using syscalls. And we get this cheap and efficient prediction and update mechanism that we can use in user space and use inside the kernel. Thank you for listening, and I'm happy to take any questions.